Yan from Tsinghua. He tells about the growth of SYK models. Please take it away.
Okay. So first of all, thanks for the invitation. Yeah, so today I'm going to give a talk about our recent work with Qiming Chang, Yiming Chen, and Zhenbin student Bi-Song Xie. The paper was on arXiv last week. So let's start with a few motivations and backgrounds on why we are studying this problem called fortuity in SYK. Maybe the first thing I should explain is what is fortuity, right? As we all know that recent years we have uncovered many quantum property of black holes, especially its property about related with quantum chaos. Those developments are mainly concentrated for the regular black holes. The black holes are not supersymmetrics and have finite temperature and energy. But recently, there was a new property called fortuity was discovered for the BPS black holes. The fortuity for the BPS black holes distinguish the microstates of black holes with states with horizonless geometries by relating the BPS states in the dual theory as you vary the rank of the gauge group N. And in our work, we're trying to understand better what is the notion of these fortuities for BPS states, and understand better its connection between fortuity and quantum chaos. So that's the background. So here's a brief outline of my talk. First, I'll give a brief introduction to fortuity. This is a word that defined by Qiming Chang and Yingxuan Lin. And then we will discuss fortuity in a simple model, which is an n=2 supersymmetric SYK model. And here we want to stress the important phenomena associated with the fortuity state, which we call R-charge concentration. And then we will talk about the R-charge concentration in a more general model or more specialized model, which is called two-flavor SYK model. And we discuss its implication for N=4 super-MLs. And later on, we make a further numerical discussion about the fortuity BPS states with quantum chaos. Please stop me at any point if you have questions. Okay. Is the volume clear now? I'm trying to speak loud here.
Yes, we can hear you.
Okay. Now let's start. Now let's first give a brief introduction to the fortuity phenomenon. The fortuity is a special property for BPS states, and that's based on two features of larger holographic theories. The first is a standard duality between BPS state and Q cohomologies. Based on the Hodge theory, one can find a one-to-one correspondence between the BPS states and the Q cohomology of the supercharge, where the Q cohomology is defined by all the Q closed states pushing out the Q exactness. And the second is special for the large N holograph theories. Namely, you can find the Hilbert space Hn for the finite N theory as a quotient of the infinite N Hilbert space by certain equivalence relations. So, namely, you can first take the N goes to infinity limit and to discuss about the Hilbert space at the N of H infinity. And then the finite N Hilbert space, this H capital N, is related by H infinity by quotient out the equivalence relation. In the case of N=4 super-MLs, this In is a trace relation between the product of the traces of the matrices. And this quotient defined a quotient map pi, and this quotient map is commute with a supercharge Q. Okay. Now, yeah.
In your previous slide, when you wrote that H infinity quotiented by this equivalence relation, the H infinity, the Hilbert space at n equal to infinity are these matrices which are infinite cross infinite dimension. So what does it mean that you are imposing this equivalence relation, the finite n? Can you just?
So the H infinity is the Hilbert space. I think it's more precisely called should define just think about the vector space. H infinity is built out of a product of traces of your gauge fields and matter field and fermions without so that's by definition is H infinity, and Hn is the same as H infinity, but now this product of traces may have some equivalence relations, so that's a quotient.
Okay. Thanks.
Thanks for the question. Okay, now based on these two properties, people Qiming and Yingxuan find that I think Qiming and Yingxuan find that there are two classes of Q cohomologies. Let's label the Q cohomology class psi represent a state. Psi n can be lifted as a psi n tilde. This lift may not be unique, and you just look for one such uplifting. Let's call it psi tilde. So the finite n state psi will be related to the infinite n by this equation. Okay. Now, being a Q cohomology, finite n Q cohomology means Q psi need to be 0, and that means Q psi tilde actually should belongs to the In, the trace regime. Now, there are two possibilities. Depends on what's the result of Q psi tilde. The first is that Q acting on psi tilde is 0, and we define the monotone cohomology as long as you can find such a lift of psi tilde, such that Q psi tilde equal to 0. And it could be a situation that you can never find such a lift, and so that defines the fortuitous cohomology. Namely, for finite n cohomology psi, you can never find the lift psi tilde at H infinity such that Q psi tilde equal to 0. So that defines the notion of a fortuitous cohomology. Okay. Now, based on these two properties, one can make understanding about the behavior of this two different class of cohomology as you vary n. So let's consider a sequence of cohomologies that depends defined by a label by n, and here you get a sequence of cohomology as you increase the n from n to n plus 1 to n plus 2. Then, based on this definition of the monotonous cohomology, you know that Q psi tilde is 0, and that means if you act on by the projection pi n, due to the commutation relation between the supercharge and the projection, this state will be Q closed automatically, and therefore you'll find that you have an infinite n limit of the BPR's operators for the monotonous cohomology. On the other hand, if you have a fortuitous cohomology, then you will find this property will be failed. For that, you need to use two properties of this trace relations. First is that if you have a matrix with rank n by n, then its trace relation In plus 1 is a trace relation for n plus 1 cross n plus 1 matrices, and that trace relation is automatically satisfied by the n by n matrices, because you can always enlarge the matrix by adding zeros. And so that's the first property. And the second property is that when you take n goes to infinities, then you don't have any trace relations. That means for any elements in IN, there exists a large enough n prime such that IN is not part of the trace relations of IN prime. Okay. That means if Q per side tutor is is given by a trace relation, you can always look at a large enough n such that this is no longer Q closed. So that means for such a BPS state, as you increase n, at some point this state will no longer be BPS and it will become lifted into a non-BPS state. And that so that's a pictorial difference between the monotonous cohomologies and the fortuitous cohomology. Yeah. Are there questions?
The motivation is that for instance, for monotonous cohomologies, you expect states like gas of gravitons or something to have.
Yeah, I'll come to that in the next slide. Yeah. Yeah. Yeah, here just a current status about this two difference of Q cohomologies in the case of angle for super Mills. Other monotonous cohomology was found by the paper by Qiming and Ying, and later on a few classes of fortuitous states was found by these two groups. So now comes to the question in the audience. So what's intuition about these two different class of BPS states? So this is a conjecture by Qiming and Lingxuan. They conjecture that the monotone states is due to the horizonless geometries, and at n goes to infinity, those are the graviton states. And but for the fortuitous states, they conjecture that it is due to the typical black hole microstates. Basically, the evidence is by some counting argument. They find that I think this was the first relation was already found out by Xiying and Qiming, that when you take n goes to infinity, the partition function of the monotone state agree with the super graviton partition function. And now you can look at the half BPS monotonous operators, and those partition function agrees with the geometric quantization of the LLM geometries, which is the horizonless geometry. And you can also count the number of monotonous states, and you find that it's much smaller than the number of fortuitous states. And yeah.
Sir, I have a nice question. So when you say that fortuitous states are typical black hole microstates, we don't expect there to be any edge cases of like very regular states which happen to have a horizon. Like we don't expect that sort of a scenario. They all have to be very chaotic states.
I couldn't hear the question very well. Are you asking about why monotonous states can not have horizon, or why fortuitous states can have horizon?
And from what I understand, the intuition is that black hole states have to be some special arrangement that you have to do independently at every end, as opposed to horizontal states, which you can have some sort of universal interpretation that works for every end. So I'm asking if there are such things as non-typical black hole microstates. Okay.
Can you come closer to the microphone, because I couldn't hear the question. Yeah.
In fewer words, say it in fewer words. Say exactly the question.
I was asking if the I was asking if there are edge cases which are horizon. I suppose that's exactly I'm asking the conjecture is true in some sense, but I'm asking if there are edge cases which are black hole microstates, as in they have a horizon, but they're not typical. They're not typical in the statistical sense.
they're not typical in the what sequence?
The statistical mechanics sense. I'm asking if there can be a possibility of such states.
Oh, you ask whether there can be special black hole microstates which are monotonous?
Yes. Like, does a horizon necessarily imply them being typical?
Area of the horizon will tell you that.
Oh, okay. I think probably not, yeah.
But that's essentially the conjecture, right?
And I think the idea will be that all of these black hole microstates, when written in terms of these simple letters, will be very chaotic. A little like the what is it called? Whatever, this one, famous conjecture. Thermalization. ETH, a little like ETH.
Yeah, eigenstate thermalization hypothesis. Yeah. Hey, Shrat.
Zhenbin, just to check, 5 by 3 comes because there are 2 derivatives and 3 scalars. So the gravitons behave like a 6-dimensional gas. So E goes like so the entropy goes like e to the power 5 by 6. That's the origin of 5 by 3, right?
Yeah, I think so. Yeah.
Okay, thank you.
Yeah, counting the supergraviton states. Yeah.
Right, but the supergraviton states behave like a 6-dimensional gas because there are 2 derivatives and 3 phi's. Is that correct?
Probably that's one way to understand it.
Okay, yeah, thank you.
Okay.
How's the
computation? Yeah.
Yeah, how's the computation of log of fortuitous given as n square? Is it analytically computed or just shown numerically?
That's by definition, because the fortuitous state means the other state that's not monotonous, and right. Yeah. Yeah, as showing these slides, the only explicit known fortuitous states are for the SU2 and SU3. So if your question was whether people explicitly find that e to the n squared number of fortuitous states, that answer is no. But I don't think that's a practical calculation, maybe. Okay. So the argument based on the relation between monotonous states and horizon. Okay, I think there's still possibility that the fortuitous states contains not only the black holes, maybe some other things we don't know, but at least they should contain the black holes. And the argument that the monotonous states and the horizonless geometries, they should be related based on this conjecture that you can imagine when you take G Newton goes to 0, then the horizonless geometry have a smooth limit to the non-interacting gravitons. But for the BPS black holes, such a smooth limit does not exist.
How does this work? Okay, I'm kind of pitching. How does this work with the string star story? So if I recall, in at least in ADS 4, I think there's supposed to be an open problem which asks if these black hole states continuously go into string stars.
What is a string star?
Oh, I'm sorry. Horowitz 60 solutions, which I think the horizon does right.
So I think the question is how does this story connect with Horowitz-Polchinski?
Yeah.
I think the Horowitz-Polchinski is for high finite temperature geometries, not to the BPS.
Yeah, sorry.
Okay. Okay, now well, we're still in the process of reviewing existing works. So in the summer, there's this work by Yimin Chen, Henry Lin, and Steve Schenker, where they propose like a more dynamical information about to distinguish this fortuitous states and monotonous states. I think the motivation was trying to have a sharp difference, more like physically sharp distinguish between those these two kinds of BPS states. They conjecture that the fortuitous state should be strongly chaotic, while the monotonous states are at most weakly chaotic. They make more precisely, they talk about the behavior of so-called Thoros time, how the Thoros time scale with n for these two different states, and that is related to this paper by Lin, Madasina, Rosenberg, and Shan. In their paper, they did some numerical check for the monotonous states, while and show that it's weakly chaotic, but the question of whether or not the fortuitous states are still strongly chaotic was not explicitly checked. They provide some motivation, pictorial argument why the fortuitous states should be strongly chaotic, based on the behavior that the previous behavior that the fortuitous states can be thought of as an invasion from a non-BPS state into the BPS sector, and therefore they should carry the chaotic property of this non-BPS black hole states. But one would like to have a more explicit examples of such invasion phenomena and or more numerical checks about this claim. So that's also part of the motivation of our work. Okay. So that's all about the introduction of the fortuitous phenomena. Are there further more questions before I go to our work? Okay. If not, then let me continue. So in our work, we studied those BPS states for various SYK models. And what we find is that basically almost all the BPS states in the SYK are fortuitous, and they share some very distinctive features as BPS states, which we call R-charge concentration. So first, the n equal to 2, let's discuss the original n equal to 2 SYK model, which consists of, it's a quantum mechanics system with n complex fermion per psi I, and the supercharge Q is made out of the 3 fermions, per psi I, per psi G, per psi K, where C is a random coupling constant. Okay. Traditionally, people would, when you study SYK, you take an ensemble average of the supercharge. But in our work, we will not do any ensemble average, but specifically focus on single realization of the SYK coupling constant. So what is known about this model? So first of all, if you allow ensemble average, then you can solve this theory in the larger limit by working on the Schwarzian equation. And you will find that the theory has a maximum Lyapunov exponent, and at a low temperature, you have effective theory described by the n equal to 2 super Schwarzian theory that is due to n equal to 2 GT gravity. The thing super Schwarzian theory also appears as the near horizon regime of the BPS black holes. Okay. I think there's and moreover, you'll find that the work by Fu, Gaeto, Madasina, and Sachdev, they find that in the n equal to 2 SYK models, all the BPS states are concentrated at the regime with maximum fermion on the fermionic charge sector with maximum number of states. So notice that this theory have a U1 symmetry, which is a number fermion number of per psi, and they find that all their BPS states are concentrated in the sector where you have n over 2 fermion excitations. Okay. One can apply our previous classification of fortuitous and monotonous on Q cohomologies into the SYK model. But in the SYK model, this is a little bit tricky because this coupling constant CRJK, its normalization actually depends on n, and we actually don't find a natural limit of defined with infinite n Hilbert space. So in our work, we use an alternative definition that is by trying to construct sequential lifts of this n. So we can consider the SYK at a finite n, and then consider the uplift to n+1 and n+2 and so on, and ask what are the BPS states allows you to sequentially uplift it into a large enough n, and those we call monotonous states, while the BPS state cannot be lifted to a large enough n. So are the fortuitous states. So if you do these constructions explicitly, then you'll find that there's a simple criterion for the fortuitous phenomenon. So here we start with a simple state, which is a state with no Fermat excitations. That we call the vacuum state. And then you'll find that if the state is monotonous, that could only be true if the number of Fermat excitation is fixed with respect to the vacuum state. Okay, maybe better I write it. So we define omega as a state with all there's no Fermat excitation or spin down, because a complex fermion could be thought as a spin. And then you can build states on top of this simple state by acting on fermions. Okay, I, J, K, etc. Okay, and you ask whether this operator could be whether this operator, if it is BPS, is a monotonous BPS operator or fortuitous operator. And the simple criterion for being a monotonous is that the number of the fermions cannot change when you do the uplifting. While if it is if the number of fermions changes, then those states will be automatically fortuitous. Okay. Now, as I said before, that since in the SYK model, all the BPS states are concentrated at the value of the when you have n/2 Fermat excitations, that means when you're changing n, this number of Fermat operator has to grow linearly with n. Therefore, all the BPS states are in the original n equal to 2 SYK are fortuitous.
Sorry, this computation was done by computing the thermal partition function and then taking the zero temperature limit?
That's right. And they also, yeah, and you can also find this behavior by looking at exact diagonalization at finite n. Okay, then you find that at a small value of n, they already concentrated at n/2, and then they check a few value of n, they find a rule, and they extrapolate to n equal to infinity. That's not hard to work out. So yeah, that actually will give a kind of a qualitative understanding about this phenomenon that all the BPS states are concentrated at n/2. We think this behavior of the concentration of the BPS states follows from the genericity of the SYK supercharge. So here, omega is the off-spin down state I described at the beginning. And so any state can be built out the omega by acting a number of fermions. And because the fermions are antisymmetric, you can base it as a P form. And now the supercharge takes is also a free form. And when you're acting on this alpha, you can think of it as a wedge product of a P form to a P+3 form. Okay, now let's look at the sequence of various the number of states carry p fermions, and if you look at the dimension of the each of the space we call omega p, then you find that the dimension first grows and then saturate at n/2 and then goes down to 0 when you take the n form. Okay, this is because of the charge conjugation symmetry. Okay, now now let's consider the action of supercharge on a generic p form field. So, for example, if a supercharge acts on this 2 form, it maps to a 5 form. So you are mapping from a smaller Hilbert space dimension to a big Hilbert space dimension. And being generic in the C3 is a generic 3 form. And when you look at this Q closed equation, we expect that generically this equation could only have a trivial 0 modes. Those are the Q exact forms. Okay, that means there should be no Q cohomologies. On the other hand, and similarly,
Zhenbin, just to make sure I'm understanding the argument, is the argument that that the state be Q closed is as many equations as there are states in this 5-dimensional in this 5-form cohomology, whereas the number of variables was the number of states in the 2-form or 3-form cohomology, and therefore you have more equations than variables, and so you shouldn't expect solutions. Is that the argument?
I couldn't hear you very well. So you had the 3-form maps from a 2-form to a 5-form, right?
Yes. So yes. So let's say a 3-form maps 2 to 5. Now, if you want the condition Q on 5-form is 0, the number of equations you have is the number of states in the 5-form space.
Yeah.
Whereas the number. Yeah. Right. Q acting on 2 forms. Sorry. Yes. Whereas the number of variables you have are the number of 2 forms.
Yes.
So you have more equations than variables, and so you expect no solutions.
Right.
That's the argument.
Right, that's right.
Okay, thank you.
That's right. Well, yeah, that's right. Yeah, but I should confess that it wasn't. It's not like a proof because it's just expectation because it's not a literally generic map because the Q squared equal to 0 condition. Okay, so.
Yeah, thank you.
But you can check that numerically. It indeed is true. Yeah. Right. Okay, then you can apply the same argument by basically you can think about Q dagger on this other hand. So for this SYK case, we expect that. Oh, sorry, I forgot to say. And this argument breaks down near the top of this this map because now you this dimension you are mapping from a bigger space to a smaller space. Then that could have a that will force you to have a large number of zeros. As the example you can see here. Okay, so that means in the end you expect there be no BPS stage when the fermion number is smaller than n/2 or bigger than n/2. That leaves you only 3 non-zero sectors. 3 sectors could have a non-zero BPS states. Okay. The reason why you have a 3 sectors is because Q is a 3 form. So actually, you have a 3 cochain complex, and it's localized at each cochain complex because the fermion Q have a 3 form. So you have 3 cochain complex from 0 to 3 to 6, and 1 to 4 to 7, 2 to 5 to 8. So each cochain complex, you only have 1 sector have a non-zero BPS state, but then you have 3 cochain complex, you get 3 sectors, you have a that contains BPS states. Okay, so that's a rough picture about what's happening in this model, that microscopically the BPS states want to concentrate, don't want to spread into other sectors. Okay. Now, now here I want to what we want to stress that this concentration phenomenon is quite universal. First of all, this above argument is valid for each typical realization of the SYK model. So you can just draw this random coupling constant randomly by another draw, then you'll find the number of BPS states will not fluctuate. It does not have a sample-to-sample fluctuations. Moreover, this concentration phenomenon could be exactly derived using the super-Schwarzian description, and that was done by Stanford-Witten. You find that the super-Schwarzian is one loop exact, and when do quantization, you find only the sector that near n/2 have non-zero BPS states. And as we mentioned before, that the super-Schwarzian description is a universal sector of BPS black holes. And third, we want to emphasize that this is the Schwarzian prediction is very strong. Like it dominates over all possible stringent corrections as long as alpha prime is finite. This is because, as you all well know, that the Schwarzian complete constant have one of the beta J enhancement, and near the BPS state, you take beta goes to infinity. So the Schwarzian effect actually dominates over all the finite alpha prime corrections. I just remind you that, for example, you can look at the correction to the Lyapunov exponent. Then it was shown by Huan and Douglas that because of this near-extremal geometry, the alpha prime correction to the Lyapunov exponent always goes to 0 when you take beta J goes to infinity. Okay. So this this box picture actually suggests that this concentration of BPS state is quite a universal behavior, and one might wonder what is the underlying microscopic reason for this concentration. And based on
are you saying it's universal in SYK or more generally?
More generally. Yeah.
Okay.
More generally, based on this bulk argument.
Well, just to ask about that. In n equals 4 Yang-Mills, for instance, the supercharge is a single trace operator. You could presumably build things that carry the same quantum numbers that are multi-trace. So it's somehow very special. It feels a little more special than your model, where if I understood right, the most general fermion number 3 operator could be written as a product of three size. So, I mean, different models may give you more special supercharges, and then this counting argument would get less and less valid. Is that?
That's right. But for that case, it will be better to develop a boundary, like a field theory argument why those the supercharge looks very generic in those sectors, which we believe is true. My personal opinion is that because acting on the fortuitous states, you want Q acting on the state to be like a trace relation, right? And the trace relation itself is very chaotic. So that means those fortuitous states, if you look at those fortuitous states should be as random as those trace relations, which is very spread. Now, then this special feature of this single trace form of the supercharge may not be that important for those fortuitous states. in the larger universe.
Okay, thank you. Yeah.
Yeah, but here I'm just talking about some bulk arguments, why this is a very universal. Okay, yeah. Right.
Sorry,
So
just to ask again, this argument is, does this bulk argument can this bulk argument in particular be taken as a bulk derivation of the fact that the number of supersymmetric states does not depend on lambda, on coupling?
I think this bulk argument should be a derivation of the number of BPS states should not flow with BPS black hole state should not flow with lambda, because this first, but not generically for the monotonous state.
Okay, yeah, thank you. Yeah.
Right. Okay. So one might wonder whether this universal property is coming from something much deeper, right? Such like random matrix universality. And that's what we wondered, and we thought this may be coming from random matrix theory, but actually it's not. So that's a very interesting puzzle. So we ask the following question: if you just give you a random matrix, and that satisfies this nilpotent equation, so satisfies the n equal to 2 supersymmetric algebra, q squared equal to 0, what will be the typical distribution of its BPS states? And if you carry out this analysis, then you find that instead of want the BPS state to have this R-charge concentration, what you find is that it wants R-charge spreading instead of concentration. And in the recent work by Turach Witten, they built a random matrix theory with n equal to 2 supersymmetry that is due to n equal to 2 GT gravity. They put in by hand this conditions of R-charge concentration. So this still, I think this is a still very important conceptual puzzle and interesting paradox to study. But in our work, we think this discrepancy may be because the supercharge in the n equal to 2 SYK is Q local instead of being actual generic random matrix. Okay. If you're interested in why this genericity wants R-charge spreading cell concentration, I'm happy to discuss more at the end of the talk.
So just to make sure I'm understanding, you say if you don't put a Q local condition, then generically you would expect a supercharge whose Q is of order n, and therefore there will be no concentration. Is this right?
Q of order n? What? Sorry, what?
The number of fermions. You had a Q equals 3 model.
Yeah.
But if you put no constraint, you could get Q, let's say, n by 4, and then there will be no concentration. Is this the idea?
I think it's not that. Yeah.
Oh.
Yeah. It's not that. Right. Because in that case, we still expect it to concentrate in a single co-chain complex.
Okay. Okay.
Yeah.
Okay. But then when you sum over all Qs, you lose this single co-chain kind of idea, right? Because
but you also want to have an R-charge. Yeah. You want to have the asymmetry, so you cannot just.
Okay.
That.
Thank you. Thank you.
Yeah, but okay. Basically what genericity tells you that there should be no nearest neighbor BPS states, because otherwise those will lift into a long multiplet. Okay, so by spreading, I mean you want for example, this sector has BPS state. Yes, this sector have no, and this could be have 0. And 0, 0, no BPS state, then there could be also BPS states, something like that. Okay, that's spreading. But the R-charge concentration is you do not have all those BPS states will concentrate at one particular sector. Okay.
just to understand, so the random supersymmetric model you're building has a Q with a definite R charge, or with a spread over R, with a definite R charge. Okay.
Definite R charge. R charge equal to 1. Yeah.
Okay.
Okay. So this basically is our conjecture. So in order to basically solve this dilemma, so we conjecture that if you want Q to be built out of Q local operators. Sorry, I forgot to mention one thing. The reason why you want R charge spreading instead of R charge concentration is that the supercharge Q1, Q2, Q3, Qn in this random matrix model are independent. You allow them to be like independent matrices except this nilpotent constraint. But that's not a property of SYK. Being Q local, that the Q1, Q2, Q3, Qn, they all take the similar same form. Okay. So once you allow that, then this optimization problem is different. And so we conjecture that if Q is a generic Q local complex supercharge, and that satisfies this equal to SUSY algebra with asymmetry, and then in the quotient complex where you have a microscopic number of index, then in this quotient complex, all the BPS states should satisfy this R charge concentration. And moreover, once you have such so many number of BPS states in the larger limit, then those should form a black hole, and then you have the you will have the dominance of the equal to super Schwarzian theory. So in other words, near those BPS states, this generic supercharge should be approximated by this random matrix ensemble of Tourette-Witten, which is due to the equal to JT gravity. So that's basically our conjecture. Okay. So if we assume this conjecture is correct, which is true in the SYK model, then you can have a few nice results just directly based on this supercharge chaos conjecture. First of all, since all the number of states are concentrated, that means the index counts the total number of BPS states. There's no cancellation. And once the index, there's no cancellation, then you can determine the location of this of the BPS states in the R charge directly using the index. So basically, because the index is projected quantity, you can calculate it in the UV or IR, but in the IR, it's all controlled by the sector with a single value of R charge. Then by taking a larger limit, you can able to read out the location of this R charge sector as an imaginary part of the index.
Zhenbin, sorry to interrupt.
Yeah.
Suppose in your integral you'd replaced I pi, you'd replaced I pi by 3 I pi.
Okay.
That would still be -1 to the R.
Yes.
But then continuing with your logic, you would get instead of a pi, you get a 3 pi. So I'm just trying to understand this argument.
Let me think. So you will think e to the I 3 pi of R.
And then what happens?
The three I pi that auto shift to the R star, but I'm not sure you'll get the same value.
Yeah, you probably won't. So the question is, why are you using I pi rather than minus I pi or 3 I pi? Or, what are the rules?
Right.
Yeah, he's just leaving the final answer. He's leaving the final answer.
Yeah.
Let's say I know the index. I'm going to figure out.
Okay. I need to think more about that. Maybe get back to you later. But
okay.
I think,
thank you. Yeah.
Yeah. But I think more generally, you don't need to like have this analytic this integral representation. Once you have some index, right? You look at the face in front of it, then you can just, and if you have a sequence of this n, then you can able to, based on whether it's plus or minus, as you're changing n, to read out how the face changes as a function of n. So for example, this one you can approximate as a cosine function, and you have if you have another, like if you are your R is like n/3, then you'll find that if you plot this sign, then you'll find on average you have a 3. As you change n by 3, then you'll find that the sign changes. So I'm not so I think once you generically you're able to once you have the theory, you have the index as a function, then you're able to read out its face depends on him. But that so for example, if the location of R was concentrated at n/2, right? Then you expect that the index as you increase n, it should on average change their sign when you increase n by 2 units.
But how can you distinguish between n/2 and n/2 plus 1 from this phase?
You don't distinguish it. You only care about the leading scaling of n.
Okay, but how about n/2 plus any integer? So maybe I didn't understand. I can ask you later. Go on.
Yeah, you can plus any integer, little n, but this argument only look at the leading scaling with n.
No, but that integer could also scale with n.
The integer also scaling with n. Then
Yeah.
you will have so for example 1/2 plus n times n, right?
Yeah.
Then the change of the alternating sign will have another, not as a function of n, will have another period, which is the inverse of 1/2 plus n.
I didn't. Okay, I will come back to this later.
No. Let's figure this out in real time. You guys are not in the time constraint is not very strict, or is it strict?
No time constraint. Please go on.
Okay. Okay. I just realized that I'm already finished my used up all my time. So.
But please just go ahead. Yeah.
Okay. Right. So let's say we assume that R have a scaling with n. Okay. So let's say if R is alpha n plus beta plus dot 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 when you take n goes to infinity. Right? Okay. So now because we assume that we know the I as a function of n, so you look at -1 to the R. And you plot it as a function of n, then you'll find that so you only look at the sign of the index. Then you find that as you increase the n, by a few units, it will will change the the sign in front of the index will change, right? Will flatten. Right. And in particular, alpha, let's say alpha is smaller than 1, right? Then this change of this the alteration of the sign will have a period given by inverse of alpha, given by 1 of alpha, right?
Yes.
Right, and that's so you can basically that's how you read out to this scaling of alpha with n.
Thank you.
Yeah.
Thank you. Yeah.
Is that I'm not sure whether the thank you means satisfied or you just want me to move on. Okay.
I'll send you an email about this. I'll think about your answer. Yeah.
Okay. Okay. Now let's so in the original SYK, there's no monotonous states, and in my process, although it does not have any other conserved UN charges, you can try to extend this analysis for more complicated model. So, for example, there's this model of given by Hedman, Turiach, and Zhao, where they propose a SYK-like model for 2 fermions, psi and chi. The supercharge Q now carry unit R charge. Okay, so that's a form of Q, and it changed the fermion number of psi by 2 units and changed fermion number of chi by 1 unit. Okay, so there's a global U1 symmetry which is denoted by J. Okay, so you can also study this model. And we will in particular focus on so this model have some like simple BPS states, but the majority that only build out of the precise fermions, but the majority of the BPS states have both psi and chi excitations, and those are fortuitous. And here we show exact numerical diagonalization of this model. When n equal to 9, so 9 psi fermions, 9 chi fermions, and you'll find that these numbers are the number of BPS states. So, and if you look at a single quotient complex as drawn by this dashed line, since the Q increase the fermion by 2 and decrease psi by 1, then you find on this quotient complex, there's only 1 sector has BPS state. So here is 3,231. And you can do a Largian analysis where you'll find that in the Largian limit, other fortuitous state will have concentrated in this codimensional 1 plane in the possible value of R charge that denoted by this this red line. This red curve you can think of as a Largian limit of this what's called the red blocks on the right hand side. Okay, and okay, and there's 2 ways in this SYK model to determine this red curve. So the first is doing this index calculation. So you can work out the index and then taking in the Largian limit to read out the phase in front of the index. Okay, that's in that way you can derive this location of this red curve. Another way to derive this location of the red curve is by solving the Schwarzian equation. So you have this. You can write down the Schwarzian equation in this model and then solve the supersymmetric solution in the limit of beta goes to infinity. This is the analog of solving the Einstein equation, and you can also find that all the BPS states, the super conformal solution are concentrated on this red curve.
So the first argument, the first argument from the index use the argument you presented 2 slides ago, right? I mean, going from the index to thank you. Yeah.
Yes. Yeah. So this is an analog of this situation in the n equals 4 case, where if you solve this supergravity solution, you find that the BPS black holes all they form a codimensional 1 plane in the possible value of the charges. And here we find that something exactly analogs happens for these two flavor SYK models. And moreover, based on the exact numerical analysis, diagonalization of this problem, we find that this concentration is even sharper. It's not just like at coarse grain level, the BPS state concentrated at this red curve, but microscopically, there's only one charge sector on a cochain complex that supports the BPS state, in line with this supercharge chaos property. Okay. So one can apply the same. So that's what we do in the SYK model, and we can assume similar phenomena happens in the n equals 4 case, where you have this BPS black hole satisfied with a nonlinear charge constraint, like this curve, red curve in the two flavor model, and then in the let me skip by these slides because you guys already know what it is. Then you by assuming that the n equals 4 case also satisfies the R charge concentration near this fortuitous state, then you can derive this location from the index. But that analysis was done in the literature using the I-optimization procedure. Here we give here what we are trying to do is to give a more microscopic interpretation of this procedure of I-optimization, where we think actually for the n equals 4 case, the BPS states are also microscopically concentrated in this around this cochain complex when you fix all the other charges. Okay. Now in the end, let me just quickly gloss over the go over the numerical analysis of the SYK model about the chaotic property of the fortuitous state. Before that, you can do a further deformation of the two flavor models such that you also contains those monotonous BPS states. So you can symmetrize of the last two index in the two flavor model, and you find by this symmetrization, this theory have a family of monotonous operator given by this V alpha beta, and those V alpha betas they form SP2K algebra, V algebra, and consequently the monotonous states in this system form a repetition of the SP2K algebra. And the simplest case, when k equal to 1, they form a SU2 algebra, and the monotonous state form a spin n representation of the SU2 algebra. So here are the distribution of the BPS state in this modified two flavor model. So the new phenomenon is that there's this one state, which is this given by this monotonous state, and in the larger limit, this monotonous state are concentrated on the curve with the same number of psi and chi. Moreover, you can look at this monotonous state; they do not satisfy this R charge concentration around this yellow complex. There's two BPS states concentrated. Sorry, there are two sectors, nearby sectors that have BPS states. And actually, we do expect this monotonous state should have a nearby BPS state because we're under generic perturbations such that you do not, the last two index are not symmetrized. Then the supercharge should only contain fortuitous state. That means the monotonous state must lift into a long multiple by a nearby BPS state. So that's argument. Now you can do a numerical analysis to distinguish the fortuitous state and monotonous state. One thing is you can project a simple operators into the BPS sectors and ask whether the simple operator should exhibit random matrix statistics. This is related to whether the eigenstates are chaotic or not, as Schwarz was mentioning. So in our analysis, we look at the charge sector. You have total number of 5,000 number of states, and the dimension of fortuitous states is 1,800, and the dimension of monotonous states only grow polynomially and only have 15 states. So if you draw the histogram of the projected operator without any projection, this operator have two single eigenvalues, and if you have projected into the monotone state, you'll still find that there's degeneracies. But if you project into the fortuitous state, you do not find the degenerate eigenvalues, and you can also study the spectral form factor of this projected operator, and you find this nice behavior of random matrix. Okay, there's some other quantity you can calculate it. That's study how chaotic this state, how spread this state in the original fermion basis, and you find that the monotone states are not that spreaded, and the fortuitous states are very the spreading is very close to the hard random state. Okay, you can also calculate the integral entropies. Also, there's difference. Okay, now let me summarize. Sorry for go over the time. I'll just let you read. A few interesting future direction is that here I didn't discuss much about this addressing of the fortuitous state with the monotonous operators. Based on the property of random matrix, we do not expect it there should by addressing a monotonous operators, you can have microscopic nearby fortuitous states. But in other words, based on this chaotic property of the supercharge, the number of the BPS states kind of repel a little bit. But there could be a mechanism that are very far away in your cochain complex. You have other fortuitous states, and that is related to this dressing phenomenon that Schwarz has been advocating. And we think it would be better to understand better this dressing between fortuitous and monotone states. And one can do it's also better to understand in the bulk whether the Schwarzian fluctuations will affect this separation of scales by addressing a very large angular momentum gravitons. One nice features is that in this model, in this new two-flavor models, you cannot address the fortuitous state by monotonous operators. For example, if this fortuitous state, if you just by monotonous operators, then you don't find any new BPS states. Okay. Okay, and
sorry, Zhenbin, but roughly speaking, your model captures what's happening in the near horizon geometry of the black hole.
Yes. Right.
And the addressing we expect is by states that are outside the near horizon. So
yeah.
So it seems consistent to me that in your model you don't see this dressing, but it might be that in all of n equals 4 super angles, you would have it. Do you agree with that?
Yeah, I agree with that. But the question is how close you can make the dressing, how small the angular momentum you can.
You can come near. How near you can come to them. Yes.
Yeah, I think in a string slide you imagine that this dressing can fill up all the planes. I think we will see that. So, for example, you have this monotone like the BPS state. There's some like what you call this valley where you cannot do this dressing. Maybe
Yeah.
over here, but not very nearby.
Yeah, it's a little like this no hair property that Seok Kim and Unwoo and
That's
companies
That's
have
right.
found, right?
Yeah, yeah. We indeed cite that paper. Yeah. So
Yeah.
although I didn't mention.
Yeah.
Yeah. So nearby there should be no hair, but if you dress by very large angular momentum, then it should be okay. But I should ask you how confident you are about those existing of the new BPS states and yeah.
Well, that there are new BPS states, I think the most clear argument is from descendants. You know,
Okay.
in our paper, we have these states called revolving black holes. We expect these gray
Yeah.
galaxies dressing with gravitons to be the most dominant thing. But there's a simpler phenomenon, which is just take black holes and look at their descendants.
Yeah.
Their angular momentum descendants. Those guys at leading order and large N gives the same thermodynamics as gray galaxies. Because once again, just descendants, derivatives condensing gives you a sink for angular momentum. And that, I cannot see a way of avoiding that being supersymmetric. Because the supersymmetric descendants of a supersymmetric ensemble are supersymmetric. And so that's
okay.
that these states exist just follows as long as we agree that the states that make up a normal black hole are dominantly primary states, then all of them will have descendants, and just that conformal representation theory then will tell you that we get this new family out of descendants. Okay, so just that makes predictions for states as a function of 5 charges, even if there's some reason that the gravitons far away are not supersymmetric. Okay, so that's statement number 1. Statement number 2 is that for the charge, you know, at the level of probes, these duals are supersymmetric. So for them not to be supersymmetric, would have to be that the probe was supersymmetric, but back reaction spoils it. It sounds very unlikely to me, but maybe not impossible. I feel reasonably confident, but you know, it's not here. Yeah.
And
okay.
In the finite N numerics, they do find this addressing, right?
It seems to be. It's a bit of a difficult game, but yeah, we're writing a paper with a little more finite N evidence for this, which I will send you when it's written.
Okay, very good.
Okay, but can I ask you one more question, please? It's also the question I asked you over email, but I'll just ask again. Okay. These chains that you were drawing, as you know very well, there are N equals 4 Yang-Mills has similar chains. Like that the index lies along a chain. And in N equals, it seems to me that the analog of your counting problem is the following. Go to free N equals 4 Yang-Mills and count how many states there are at each point on this chain.
Yes.
Now, if I use the same genericity arguments that I understood you were using, but maybe you'll correct me, then what you would expect once again is that you should expect, your arguments would seem to suggest that you would get localization at the point where you have a maximum number of states on this chain.
No, that's not what we argue. Yeah.
Why not? So can you help me understand that?
Well, that's what because it's Q squared equal to nilpotent constraint Q squared equal to 0. If it was like literally independent, then you may think about that. But yeah, like for example, this just does not work for this 2-flavor model. So if you look at this curve, this red curve, it's not at the maximum charge sector. If I draw the maximum charge sectors, it's very close to the fortuitous states, but not they're not the same. Yeah.
Okay, but then is there, fine, so suppose I want
The
to take,
location should be determined by index. Yeah,
okay,
not by the
not by counting, not by,
UV.
yeah, so there is no independent way. So there's no independent way to look at the chain and try to predict where the. Yeah.
No, I don't find, yeah. And I think you are referring, maybe you have in mind this Finn-Larsen paper.
The Finn-Larsen paper has
I think
many,
that
in my
is
opinion, has many issues. Yeah.
yeah, I think at least their claim is not correct. Like,
Yeah.
yeah. I mean, it's just not a thing. Like the location of the R charge and the maximum charge dimension sector, they are not the same. Yeah.
Okay. Great. Okay.
Yeah.
So
you
then
can only derive it by the index calculation.
But wouldn't it be satisfying? Perhaps then wouldn't it be satisfying in your, let's say, your two flavor model? You could. Why did it work? Why did this genericity argument work in the first model but not the second one? What is the difference?
Oh, I think, yeah. So basically, that's I think so. I think maybe I didn't express this puzzle more clearly. Basically, this puzzle is saying that we don't understand the genericity argument. Like, we don't have a first principle that a generic, in what space a generic theory should be concentrated, and that's why we have this conjecture. Okay.
Good.
Yeah. Right. So in this case, here what I'm discussing is like a very imprecise argument why this in the SYK case it's localized at these sectors. And in order to actually prove that it is a generic supercharge, give you this one, we first need to have a numerical evidence that one numerical example. So one realization have this BPS distribution. Then based on that, we can show that this is generic in this space. Okay. So there's no, I think, if you are referring that we can just based on this definition and to derive that it have localized at this N/2 sector, that's not correct. We do not have that derivation, and that's that's a puzzle. That's why we need to propose this conjecture.
Okay, thank you. Yeah.
Yeah, I think it's in my mind, it's very important to understand in what space, this generic, like in what space a generic supercharge will like to concentrate. In the SYK case, it likes to concentrate, but are there, as you said, a first principle to derive that in that space it will concentrate, and why, and maybe if you understand that, you can apply it to the other case. Yeah.
Okay, thank you so much.
Yeah.
Thank you again.
Yeah.
This was an absolutely fabulous talk, and it's great work, Zhenbin. So thank you so much.
Thank you. Thanks for the comments. Oh yeah, I have one final comment. Yeah. So I used to think about supersymmetry and quantum chaos are kind of do not talk to each other. And here looks like maybe recent development means there could be a more interplay between quantum chaos and supersymmetry in this new from this new angle. So I think that probably is worth to develop more. Yeah. Okay.
Yeah, but chaos not as measured by conserved charges, but by something else.
Yes.
Yeah. Okay. Thank you.
Thank you, Zhenbin.
Thank you. Okay. Bye.
Bye.